in calculus courses, you'll learn, if you take more calculus courses, you'll learn that there's actually many ways to integrate functions, and we just touched the tip of the iceberg on integration. There's several different types of integrations that you can do, but one of the first types of integrations we talk about is integration by parts. And basically it goes like this. So let's say that u is a function of x and du is the derivative of that times dx. And let's say v is a function of x and dv is the derivative of that function times dx. Then there's a method called integration by parts, which actually says the integral of u dv is equal to uv by the integral minus the integral of v du. Now, this result still has an integral in it, but the idea is going to be that you actually, when you integrate this, that this second integral that you get is actually easier to integrate than the original one. So let me show you an example of that. Okay, so here's an example. Let's say that you want to integrate x times e to the x dx. Well, I can't use any of the techniques I had before because the x is there, and so I'm going to have to use this parts form. So I'm going to say I want this to be in the form of u dv. Okay, u dv. So I'm going to say that the u part is just the x. Well, if the u part is the x, then the dv has to be the rest of it. The dv has to be the e to the x dx. Well, then if u is x, then du would just be the derivative of that times dx. So that'd just be 1 dx. And then if dv is e to the x dx, well, you know that v would just be the integral of this. So to get v, we would integrate this. And when you integrate e to the x dx, you get e to the x. So now let's put it together in this formula. The result would be, the result of this is u, this is dv. So it says if you're integrating u times dv, then that's going to equal uv, which is x times e to the x, uv, and then minus the integral of v du. Well, v is e to the x, right? And du is just dx. Well, now this integral is easy to integrate because it's simply just e to the x dx. I mean, just e to the x. So when I integrate this, I get x e to the x, and then to integrate this function is just e to the x. So I get x e to the x minus e to the x, and then of course plus a constant. Okay, that was so much fun. Let's try another one. X times natural log of x dx. Now in this one, I'm going to let u equal the natural log. And the reason I want to let u equal the natural log is because, remember, whatever you let, what portion of this you let be dv, you've got to integrate it. And I don't really know how to integrate natural log, so I don't want it to be involved in the dv. So I'm going to let it be the u. Okay? And then if that's the u, then the rest of this, x dx, must be the dv. So that way, the natural log is the u, and the x dx is the dv. So therefore, this is actually can be u times dv. The x dx is the dv. Now, from u I can get du. We know how to take the derivative of natural log of x. It's just 1 over x. So du would be 1 over x dx. And then when I integrate this, we know how to integrate x. It's just x squared over 2. So now I want to get, let's see, what I want. What's the formula say? uv, so I need uv. So u is natural log of x, and v is x squared over 2. So there's uv, and then minus the integral of, what is it? v du. So that'd be v, which is x squared over 2, times du, which is 1 over x dx. And then notice that x squared over x is just x. So actually this simplifies to just this integral, 1/2 x dx. And so then I just went ahead and wrote these together, those two factors together. And now we know how to integrate x dx. It's x squared over 2. So I'm going to have minus 1/2 times x squared over 2 for this integral, and then I add the constant, and then the next step I just simplify this second term. 2 times 2 is 4, so the second term is going to be minus x squared over 4. And so there's your final answer. Okay, so it's seems like a clever technique, doesn't it? But it's just a method to get your integral into a form that involves another integral that's easier to evaluate. So here I'm going to let u equal the 6x. So u is going to be the 6x. And then du would have to be the rest of it. dv would have to be the rest of it. E to the minus 3x dx. So I'm going to let dv be that. Now the derivative of u is 6, so du would be 6 dx. And then when you integrate this, remember I told you before, if you integrate e to the ax, you just get e to the ax divided by a. So that's going to be e to the negative 3x divided by negative 3. Now I didn't write the constant on these because I knew I was going to write it at the end. So I'm just letting you know that. Okay, so now this is the integral u dv. And remember it's going to be uv, so it's 6x is u, and then v is this expression. So there's your uv. And then minus the integral v du. Well, v is this, okay, and du is 6 dx. So let's simplify that a little bit. First of all, 6x divided by negative 3 is negative 2x. So that's negative 2x e to the negative 3x. And then this integral, negative 3 goes into 6, gives me a negative. So I get a negative 2 e to the negative 3x dx. And now that's a, see, I have two negatives, a negative here and a negative here. So let's just change that to a plus. So that gives me minus 2x e to the negative 3x plus 2 times the integral e to the negative 3x. And again, we know how to integrate e to the negative 3x. It's just e to the negative 3x over negative 3. So you take 2 times e to the negative 3x over negative 3, and you get minus 2/3 e to the negative 3x. And then make sure you throw in your constant at the end. You notice that we generally use these when it involves logs and e to the x when we can't come up with another way to do it. So here I'm going to let u equal natural log of 5x, and then du would just be, let's see, I've got that written wrong here. That's actually going to be 5 over x dx, so that needs to be corrected. So the derivative of natural log of 5 dx, that would be 1 over 5x dx. Hang on just a second, that's not right. Okay, I had it right the first time, because if you took the derivative of this, you'd get 1 over 5x times the derivative of 5x, which is 5, so you'd have 5 over 5x, which is actually 1 over x dx. So that's right. All right, dv would be the rest of it, which is the x squared dx. And you know how to get v from that. Just integrate, and you get x cubed over 3. And now put it together. uv would be natural log of 5x times v, which is x cubed over 3, and then minus the integral v du, which would be x cubed over 3 times 1 over x dx. And this integral can be simplified to minus 1/3 times the integral x squared dx. And then all you have to do is evaluate this integral, and we know how to evaluate that. That's just going to be x cubed over 3. So then multiply it by minus 1/3, and you get minus x cubed over 9. And then, of course, you had this term already figured out, and then we bring this term down with it, and then add your c, and there's your answer. Now, there's a couple of practice problems down here that you can work on, and you might have to do a little trial and error to decide what you want your u and your dv to be in those, but eventually you should get the answers that I've got below the problems. Well, I figured I should show you a definite integral by parts. So here's one, x cubed times natural log of x dx. I'm going to let u be natural log of x, and then of course dv has to be x cubed dx. So if u is natural log of x, du is 1 over x dx, and if dv is x cubed dx, then v would be x to the 4th over 4. Okay, and then so if I do uv, I get x to the 4th over 4 times natural log of x, which is this term, and then minus the integral v du would be x to the 4th over 4 times 1 over x dx, and then that simplifies to minus 1/4 times the integral x cubed dx. And then when I evaluate this, I get x to the fourth over 4 times minus a fourth. So that would be minus x to the fourth over 16. So I've got this entire function, and I'm integrating from 1 to 4. So what I have to do is I have to evaluate this at 4. So I'd have 4 to the fourth times natural log of 4 over 4 for the first term, and then minus 4 to the 4 over 16 for the second term. But that's only for the first part of the fundamental theorem of calculus. Then I've got to evaluate this at 1. So I have 1 to the fourth times natural log of 1 over 4 minus 1 to the fourth over 16. Well, let's see if we can figure this out. 4 to the fourth over 4 is 4 cubed, which is 64, times natural log of 4. And then 4 to the fourth over 16 is actually 16. So the first expression is 64 natural log of 4 minus 16. Now the second expression, since it has natural log of 1, remember natural log of 1 is 0, so this numerator is going to be 0. And so that first term is going to be 0. And then you have minus 1/16. Well, then distribute the minus, and that becomes plus 1/16. So you get 64 times the natural log of 4 minus 16 plus 1 over 16. And then I went ahead and plugged it into the calculator and got an approximation. Now, if you want to do a couple of practice problems here, I gave you a couple of practice problems here that you can do, you can use. And this one's from 0 to 1, x squared e to the 7x dx. And then this one's from 1 to 2, x squared natural log of x dx. And I gave you the answers below them. So have fun with those practice problems. Okay, let's finish with a couple of applications. This is a present value of a continuous stream of income. An electronics company generates a continuous stream of income of $4 million per year, where T is the number of years that the company has been in operation. Find the present value of this stream of income over the first 9 years at a continuous interest rate of 12% and round at 1 decimal place. Well, the solution is, remember, if we have continuous compounding, the principal can be calculated by the amount times e to the negative RT. But we know the amount of the income is 4T, because it's 4T in millions. And then, so that's the amount, that's the principal, the amount rather. And then e to the negative RT, where R is 0.1T. So now, if we integrate this over 9 years, we would integrate it from 0 to 9 and using this function. Now, you can actually evaluate this with parts. Let u equal 4t and dv equal this. And then you can calculate du and v, but when I put it together, I'm actually going to get this answer, e to the negative 0.12t, and then I'm evaluating from 0 to 9, and so I get this, and when I evaluated it, I got 85.6 million. Now I know I left some blanks in there, but I'm running out of time, and so you need to apply a differentiation by parts here to simplify this, and then do the uv minus the integral v du to finish it. Here's another example. It says the model for the ability of a child to memorize is measured on a scale of 0 to 10 is given by this function, where t is the child age in years. Find the average value predicted by the model for a child's ability to memorize between the first and second birthdays. Well, the average value, remember, you integrate the function over the interval, so we would integrate the function from year 1 to year 2, and then we would divide by the length of the interval, which is actually just 1. So we end up just evaluating this integral. And you're okay on the 1. The 1's easy. But to evaluate the second part of this integral, you're going to have to use integration by parts. So you can take that separately somewhere on scratch paper and evaluate that second integral by using integration by parts. And then evaluate it from 1 to 2 using the fundamental theorem of calculus, and you'll get 2.018. So, hopefully you can fill in the pieces there that I left out and finish that problem. And that pretty much finishes this chapter. I've got another chapter that I might add that has some extra concepts in it.